Hi students, in today's session we are going to discuss about nuclear fission reaction. It is a process in which a heavy nucleus breaks down into two or more fragments, releasing a very large amount of energy. Here I have shown you an example of a fission reaction where a heavy nucleus, that's uranium-92-235, captures a neutron, becomes a compound unstable nucleus, uranium-92-236, which immediately forms the fragments barium, krypton, three neutrons, and a large amounts of energy is released in the process. Here, the binding energy of the heavy nucleus is released as energy. Now, the process of nuclear fission can be explained on the basis of a liquid drop on the basis of the liquid drop model. When a liquid drop is suitably excited, it oscillates in a variety of ways, and the drop becomes, instead of uh, its usual spherical shape, it becomes a prolate spheroid, then again a sphere, an oblate spheroid, a sphere, a prolate spheroid again. That means it oscillates. Now, the restoring force here is the surface tension forces. But if the excitation energy is such that the surface tension forces are overcome, then the liquid drop oscillates and it finally separates or breaks down into two smaller liquid drops. Similarly, in the nuclei, when the nucleus is excited, here again there's a surface tension force which holds the nucleons together in the nucleus. At the same time, there are repulsive forces, that is, the repulsive force between the protons in the nucleus. When sufficient amount of energy is provided to the nucleus so that it gets excited and the surface tension force is overcome, then and the repulsive force between the neutrons becomes so strong that the nuclei will split into two parts, just like that in a liquid drop. So the liquid drop model was able to explain the process of fission. Now the energy given off in a fission reaction of one nucleus of uranium is about 200 MeV. It's such an enormous amount of energy. The next term that you have to learn here is what is called a chain reaction. A chain reaction is a self-propagating process where the number of neutrons goes on multiplying in a geometrical progression that the fission reaction goes out of control. That is, a neutron, a slow neutron is captured by a heavy nucleus like uranium. It splits into two fragments together with the release of, say, two or three neutrons of three neutrons. These neutrons go and hit more heavy nuclei, say uranium. Again, they fragment into smaller nuclei together with the release of two or three more neutrons. And these neutrons uh, again undergo fission, make more of uranium nuclei undergo fission, and this process continues in an uncontrolled fashion, resulting in a chain reaction. Now, controlled chain reactions take place inside the nuclear reactors. Now, when we have to distinguish between chain reactions and controlled chain reactions which take place in the nuclear reactors, we define something called the multiplication factor K. Multiplication factor K is the ratio of the number of neutrons in one generation, that is, the number of neutrons released in one generation, to the number of neutrons in the previous generation, that is, preceding generation. So we find out the number of neutrons released in one generation divided by the number of neutrons released in the previous generation, so that you get the value of K. Depending on the values of K, three conditions can be obtained. The first one is the fission reaction may be subcritical if K is less than 1. That is, too few neutrons are there to cause fission and the reaction slows down and stops. K becomes less than 1 when the number of neutrons in one generation becomes lesser than that in the preceding generation. So that K is less than 1. So very few neutrons are available to cause fission, and the reaction slows down and it ultimately stops. Now, if the fission reaction is critical or steady, this happens when K is equal to 1. That is, the number of neutrons released in one generation is equal to that released in the previous generation. So, that fission reaction is equal to 1. Here, 1 neutron per fission is released to cause another fission, so that energy is released at a constant rate. This is what is taking place. This is the condition existing inside a nuclear reactor. Last, the fission reaction can be supercritical, that is, K is greater than 1. That is, more neutrons are released after each reaction, and the energy released will be so rapid that an explosion takes place. That is, the number of neutrons released in one generation will be much greater than that in the previous generation. So, this is the condition that exists in an atom bomb. Now, let us consider a nuclear reactor. It is a very efficient source of energy where the fission reaction takes place in a controlled manner. The fission of 1 gram of uranium-235 per day evolves about 1 megawatt of energy. The energy given off in a reactor becomes heat and it's removed by liquid or gas coolant. The hot coolant is used to boil water and the resulting steam is fed to the turbine of an electric generator to produce electricity. Now, nuclear reactor consists of 5 major parts. One is the fissionable material, that is our fuel present in the form of fuel rods, which can be uranium-92 235, thorium-232, plutonium-239, etc. The next part is what is called the moderator. As you know, natural uranium contains two isotopes. One is uranium-238 and the other one is uranium-235. But the fissionable isotope, that is uranium-235, forms only 0.7% of the total uranium reserves. Now, fission takes place only by the absorption of slow neutrons. Now, uranium-238 has a very small cross-section for slow neutron capture, whereas it captures fast neutrons without undergoing fission. That is, അതായത് uranium-238ന് സ്ലോ ന്യൂട്രോണിനെ ക്യാപ്ചർ ചെയ്യാനുള്ള പ്രോബബിലിറ്റി വളരെ കുറവാണ്. അതുകൊണ്ടാണ് അതിൻ്റെ വെരി സ്മോൾ ക്രോസ് സെക്ഷൻ ഫോർ സ്ലോ ന്യൂട്രോൺ ക്യാപ്ചർ എന്ന് പറഞ്ഞത്. എന്നാൽ അത് ഫാസ്റ്റ് ന്യൂട്രോൺസിനെ ക്യാപ്ചർ ചെയ്യാനുള്ള അതിൻ്റെ പ്രോബിലിറ്റി വളരെ അധികമാണ്. പക്ഷേ ഒരു uranium-238 ഫാസ്റ്റ് ന്യൂട്രോണിനെ അബ്സോർബ് ചെയ്താൽ അവിടെ ഫിഷൻ നടക്കില്ല. Whereas uranium-235 has a large cross-section for slow neutron capture. Okay, so what is our responsibility? We have to slow down the neutrons to make the fission possible. That is, uranium-235 has to have a large number of slow neutrons available so that fission reaction becomes possible. That is, this fission reaction becomes possible. So, what are moderators? Moderators are materials used to slow down the fission neutrons. Here, the nuclei of the moderator molecule or moderator atom collides with the fast neutrons and absorbs the energy from them without capturing them. They just absorb their energy without capturing them so that the fast neutrons get slows down. അതായത് ഈ ഫിഷൻ വഴി ഉണ്ടാകുന്ന ന്യൂട്രോൺസ് എല്ലാം ഫാസ്റ്റ് ന്യൂട്രോൺ ആണ്. അവരെ ഈ മോഡറേറ്റർ സ്ലോ ഡൗൺ ചെയ്ത് ആ സ്ലോ ന്യൂട്രോൺസ് പിന്നീട് അടുത്ത uranium-235വുമായി ഇടിച്ച് പുതിയ ഫിഷൻ റിയാക്ഷൻ ഉണ്ടാകുന്നു. So the examples of moderators are heavy water, graphite, etc. The next part is neutron reflector. Using reflectors, the leakage of neutrons can be reduced and the neutron flux in the interior can be increased. The next one is control rods, the next part of a reactor. So, control rods enable the chain reaction to be controlled, or they help to maintain the criticality of the reaction. It enables the fission reaction to take place under critical condition. That is, controlled rods are made of materials like cadmium, boron, etc., having large neutron absorption cross section. So these neutrons have large neutron absorption cross section and they absorb the neutrons and control the nuclear fission reaction. When the control rods are pushed in, then the operation of the reactor is stopped, and when the control rods are pulled out, the reaction rate can be built up. Next is the coolant system. The coolant removes the heat produced in the reactor core, and the coolant is pumped through the reactor core. It transfers the heat away from the reactor to the secondary thermal system. Example, water, steam, hydrogen, carbon dioxide, air, etc. So this is the schematic diagram of a reactor. So here these are the fuel rods. This represents the control rod which can be pushed in or pulled out. Then the more hot liquid is circulated here, and there is a heat exchanger system, and this represents the turbine of our electric generator. Next we come to breeder reactor. There are certain non-fissionable nuclei which can be transmuted into fissionable ones. For example, uranium-92-238. It absorbs a neutron, it becomes uranium-92-239. After that, it undergoes two steps of beta decay. That is, uranium-92-239 undergoes first beta decay to form neptunium-93-239. And once again, it undergoes beta decay. Neptunium undergoes one more beta decay to form plutonium-94-239, which is a fissionable material and it can undergo fission. Okay. So, breeder reactors are specially designed reactors which produces more fissionable material than it consumes. So, it produces more of plutonium 92 to 13, 94 to 39 than the uranium 238 that it consumes. Another example where a fertile nucleus is converted to a fissionable nucleus is thorium 9232. It absorbs a neutron and becomes thorium 9233. Then this thorium-9233 undergoes one beta decay to form palladium-91-233. Palladium-91-233 undergoes one more beta decay to form uranium-92-233, which is a fissionable material. Thus, a breeder reactor is a specially designed reactor which produces more fissionable material than that it consumes. So, I hope the concept of fission, chain reaction, nuclear reactors where chain reaction takes place in a controlled fashion, and breeder reactors is clear to all of you. If you have any doubts, please do contact. Thank you.